Hi all. So in this video, we will further introduce two single trajectory diagnostics, namely the so-called TRA, which stands for trajectory rotation angle, and the TSE, which stands for trajectory stretching exponent. So the TRA is essentially a measure to quantify the local rotation in the flow using just single trajectories, whereas the TSE is a measure to quantify the local hyperbolicity along a trajectory. Both diagnostics have been designed to work with sparse data. So what does this mean? Well, in the previous videos, we introduced the FTLE, the LAVD, and the PRA, and all of these diagnostics essentially required the computation of the gradient of the flow map either, or of the gradient of the velocity. So when computing the FTLE and the PRA, we had to compute the gradient of the flow map, and when computing the LAVD, we had to use the gradient of the velocity essentially, because we had to compute the vorticity. So in a sparse data set, this is not possible. So computing gradients in sparse data is complicated. As I mentioned, for example, the ocean, where you got thousands of drifters, which are, however, spaced kilometers apart. So when I'm not talking about 1 or 2 kilometers, but I'm talking about hundreds of kilometers. So in such a case, you cannot compute gradients over hundreds of kilometers. So you need to rely on just individual trajectories. We start with the computation of the TRA. So the TRA is essentially it's essentially a diagnostic to quantify the material rotation in the flow. So, sorry, let's go back. All the files are essentially located in this TRA folder, and we'll just focus on the 2D case for the moment. So we got several files. The main folder contains the main notebook, where we can run and show the results. This TRA notebook, what this does is it contains the function to compute the so-called TRA diagnostics. So how is this TRA defined? Well, you just simply you compute the velocity, you compute a trajectory from T0 to Tn, and then you compute the velocity along the trajectory. So you compute this x dot. And once you have that, you simply need to take the angle between two subsequent velocity vectors. And then you need to average that out along a trajectory. So this associates to each initial condition, so to each trajectory, basically, a unique TRA value. Now, what this physically means is that, of course, if you have a trajectory which, for example, just travels on a straight line, so does not rotate physically, then this inner product will be, so then the angle between these two vectors will constantly be 0, right? Whereas if you have a trajectory which is spinning very fast, then this inner product will be huge. So this is a bit the physical intuition that I'd like to keep here. The TRA function, what it takes as input, of course, the velocity along the trajectory. And this is simply an array of size nt, where nt is simply the number of the measurements. Of course, this is all discretized. So this is simply the number of measurements along the trajectory. And 2 simply stands for the x and the y component of the velocity. And then also the length of the time interval, because we need to normalize this in the end. What it does is it simply really implements this function here. So you iterate along a trajectory, you extract the velocities, x component and y component velocity field of the velocity at the time k, basically, and then at the time k plus 1, you do the same, and then you just simply compute the angle. So it's fairly straightforward. Now we don't focus for the moment on this extract vortex notebook, because we go directly to the main notebook, which is again, we applied this, or we computed this diagnostics for trajectories in the Agulhas region. So all the initial steps are essentially the same. The only thing I did is, in order to change things a bit, I changed the spatial domain. So I'm considering a spatial domain I'm considering a different spatial domain than in the videos of the LAVD, FTLE, or PRA. But essentially, the first 4 steps are exactly the same. Now, for the TRA computation. So we essentially first need to compute the velocities along trajectories. So we need to compute this x dot. Once we have that, we basically pass, for each initial condition, this x dot into the TRA function I previously showed you, which does the computation. Then we plot, So we basically have then for each initial condition, we have a certain TRA value, and then we plot this TRA value over the initial conditions. And what we get is then a nice TRA field. Now, since the TRA was designed to work in a sparse data setting, we then also show this ability by simply subsampling the data. So we just simply take away individual trajectories and then reconstruct the TRA field using some standard interpolation techniques. And once we've done that, we would then like to extract approximate vortex boundaries from this reconstructed TRA field. And we do this by simply running an algorithm, which is fairly similar to the one you use for extracting vortex boundaries from the LAVD. However, of course, since here we are in a sparse data setting, this would just give approximate vortex boundaries and you cannot expect to have exact vortex boundaries. Also, this algorithm relies on a bunch of parameters because you need to look for local maxima in a TRA field. You need to define how many drifters you require to be inside an eddy for it to be defined an eddy. However, we'll come to that later. So the first 4 steps are the same. What we do so when we just focus now on the TRA part, again, we basically implement this function, which is called parallel TRA, which is just a wrapper function, basically. And what it does is it takes as input the initial conditions. Now, keep in mind that in order to speed up the computations, we've basically vectorized initial conditions and put them into different batches so that we can run, so that we can compute the TRA in a parallel fashion. So this function simply just takes care of that you compute the TRA in a parallelized fashion. Now, this defines our initial conditions. We pass these initial conditions into this into the integration dfdt function, which is something we're already pretty used to. However, we do not actually need the trajectory, but we just need the velocity. So we just want to access the second argument that is returned by this integration function. That's why I've got a 1 here. And the second argument is exactly the velocity. So dfdt simply stands for the time derivative of the flow map, which is the velocity. Once we've done that, we can pass this dfdt. So we can now iterate over all initial conditions inside this batch and pass the dfdt, so essentially the velocity along the trajectories, into the TRA function we previously saw we previously saw. So this TRA parallel, of course, is now returned to the main script and then rearranged. So I'm now here basically, again, vectorizing everything, running the parallel computation and extracting then the results from the parallel computation. And then here, since it's been done in a vectorized fashion, I, of course, need to rearrange everything into a mesh grid. So that's why I need to reshape everything here. Once I've done that, I can then plot the results. And you can see there's this TRA function, which shows 3 major regions with three major regions with increased rotation. So of course, this one here, and this one here. Now, what we'd now like to do is so the first thing to do is we now start subsampling this TRA field. So we start subsampling this TRA field simply by taking out individual trajectories. So here we just take 10% of the trajectories. Here we just keep 1% of the trajectories, and here we just keep 0.1% of the trajectories. And you can see that even by taking away, so even by just keeping 0.1% of the trajectories, we still have a fairly good approximation of the vortical flow structures. Now, this eddy here disappears simply because there are no drifters, or there's no drifter inside the core of the eddy. So that's why it starts disappearing. Of course, if a trajectory, I actually generally tend to confuse drifter and trajectory, but they're essentially the same for this moment. So if a trajectory is not sampling an eddy, then I cannot expect it to be visible in the TRA field. Now, once we've done that, we would now implement the so-called TRA vortex boundary algorithm. The TRA vortex boundary algorithm is defined in the same folder and is in this notebook extract vortex. So this is simply extract vortex function. The way it is done is, of course, you need to reconstruct the TRA at some specific time instant using linear radial basis function interpolation. You need to find the local maxima. And here, when finding the local maxima, you, of course, need to specify a threshold on the local maximum. Then you compute, then you basically look for the closed level set of the TRA field around the local maxima, which has the sharpest gradients. And you need and of course you require that inside these this vortex there are at least n drifters, where n is simply a parameter you need to define. Once you've done that for each local maxima, you need to take the convex hull of all selected closed curves, and if two or more closed curves intersect, then you need to take the union of these curves. And then again, in the end, you need to take the convex hull again. So the convex hull is taken because we basically require that the eddies we get are convex structures. This is a constraint that we put on. So going now back to our main notebook, we can so we need to specify a bunch of parameters in this extract vortex boundary algorithm. So one parameter is basically the resolution we use to reinterpolate the data to the regular mesh grid. The other parameter is the threshold we apply on the local maximum, and the last parameter is the number of trajectories we require to be inside the vortex, which I set to be 2 for the moment. Once we've done that, we can run the algorithm, and you can see that on the 10% subsampling, you get all 3 beautiful vortex boundaries. Now, if you keep subsampling, then it might be that, for example, here, this vortex boundary, there is no white boundary here simply because there's just one drifter inside this eddy. So it's it is not identified as an eddy because I specified that in order to be inside an eddy, in order to be an eddy, you need to have at least 2 drifters. But still, the other 2 eddies are fairly well retained, and even on the 0.1% subsampling, basically this eddy completely disappears because there are no drifters inside the eddy, whereas these 2 guys still remain, and actually the shape that they show is fairly reasonable for an eddy. So that's it for the TRA computation. Now the TSE essentially follows the same steps. With the TSE, actually, you have 2 TSE diagnostics. So one is you simply consider the final velocity of the trajectory and divide it by the initial velocity of the trajectory, and then you simply take the logarithm. So this basically is a measure of how much the velocity vector is being stretched from time t0 to tn. And then you can do the same thing, but you would be interested in finding the average stretching. So this is at TSE bar. There, you do not consider the initial and the final. So there you do not consider only the initial and the final velocities, but you consider all the velocities in between. So this is the TSE is basically, the TSE bar is essentially a measure of the averaged hyperbolicity in associated to this initial condition. All the steps are the same, so we can now plot these 2 quantities over a set of initial conditions, and what you get is, so here we just plot the TSE, so we took the final velocity and the initial velocity, computed the ratio between the 2, and then took the logarithm, and then normalized it by the time. And of course, positive, so we distinguish here generally between positive areas and negative areas. So positive areas indicate trajectories which are whose velocity vector is stretched, whereas negative areas indicate trajectories whose velocity vector is compressed. Basically, it gets shortened. And then we can do the same thing for the TSE bar, which reveals a bit more robust structure, but you can see that basically ridges of this TSE or fronts of this TSE actually indicate or are closely related to ridges of the FTLE. Now, the last thing I would like to mention here is that both the TSE and TRA are not objective diagnostics. However, they do approximate an underlying objective diagnostics related either to material rotation in case of the TRA or to stretching in case of the TSE, and they approximate these under appropriate conditions. So one appropriate condition is that the local material rotation in the flow needs to be much, much higher than the spatially averaged material rotation. This assumption tends to be satisfied over large enough ocean domains, for example. And the other assumption is that the partial derivative of the velocity needs to be much smaller in size than the Lagrangian acceleration. So you basically assume that the advective terms dominate the unsteady terms arising from the partial derivatives of the velocity field. With that, I would like to point out to the appropriate references and also to the chapter in the book. And I would like to thank you for your attention.